Welcome, and this is Schweitzer. This is going to be a short little video on gases. Why is a gas a gas? Which is 4-3A, so it's states of matter, liquids, gases, and then 4A is dealing with the inter and intramolecular effects of gases. Um, so what are the international factors affecting the properties of gases? Students can describe and recognize the difference between ideal and non-ideal gas. That's probably the only thing that's, well, there'll be some properties only, but this is right here is probably one of our um, newest things that we want to make sure we add on here. 3-4 is inter and intramolecular forces, and we'll talk a little more about that. All right, so external factors affecting gases. Obviously, temperature and pressure are going to be the main factors affecting gases. But we also, for this one, have the volume. The volume of a gas can be compressed. So these are all the factors affecting a gas. Um, Temperature we've already talked about, pressure we've kind of talked about, but we're highlighting here one of the differences between pressure, atmospheric pressure, and pressure inside of a container. Both of these are the same units. This one literally is just weight of gas coming down on top of you, providing a force. And this one is the number of collisions inside of a container. Um, and we'll talk more about that as we move along. Both of these pressures can be equal force per area inside the container. All right, so here's some examples of some questions. Okay, and we'll add on some notes and things as we go along to make sure we can answer them. All right, so a sample of gas, O2, is initially at STP. Now make sure you understand STP in this area is going to be 0 degrees Celsius and 273 Kelvin, and that's the same thing. Okay, and then the pressure is 1 atmosphere, or it could be the same equivalent would be 760 millimeters of Hg or torr. All right, so we have a sample of gas that is compressed into a smaller volume at a constant temperature. What effect does this change have on A? All right, so there's several different options here. Um, let's sketch out a little picture of this. Essentially, we may consider this like a piston or something. So we have a little object here and a little piston. And it starts out with some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we take this piston and we just squeeze it down into a smaller area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it says at a constant temperature. That's an important factor right there. Temperature does not increase. How does this effect have on the following? First of all, average kinetic energy is well, that's temperature. How we want to know that? So no effect. Um, it's just like saying, what will this change have? How will this change affect the temperature? Well, this is temperature. B, average speed of O2 molecules. Well, since we're not changing the temperature, then we're not changing the speed of the particles. Again, no change. Total number of collisions inside the container. Well, since the particles are traveling the same speed and they're in a smaller area, they should probably collide more often. And therefore, it goes up. I also had mentioned the pressure is going to go up because of the increased number of collisions. The number of collisions of O2 per area unit of the wall per unit time. Oh yeah, this is exactly how you would describe pressure. So, again, that increases. All right, so what else do we have here? Let's go down this next question. Okay, so it says, which balloon has the highest average kinetic energy? So Looks like we're looking at these balloons right here. Okay, 3 of them. Now which one? And they're all the same temperature. They're all the same volume. They're all under the same pressure. Okay, so which one has the highest average kinetic energy? Since they're all the same temperature, they're all the same. Which one has the highest molecular velocity? All right, now this is different. This is a very important question. If your average temperature is your kinetic energy equals 1/2 the mass times velocity squared, they all have the same average temperature. But particles with heavier masses have lower velocities. So in this case, because krypton has got the biggest mass, it has the slowest velocity. And helium having the smallest mass has the highest velocity. So this answer right here is helium. So helium has more collisions with the inside container of the balloon than does krypton. Now the particles are much less massive, and therefore the collisions are not as forceful, but it takes a lot more collisions to create the same amount of pressure as it would be for the krypton particles whacking the inside of the container. All right, they're the same temperature, and they also have the same number of particles. So it'd be 1, 2, 3, 4, 1, 2, 3, 4. So which one has the highest density? Well, they're the same. So density is just mass, all right, divided by volume. And they all have the same volume. They all have the same number of particles. But the krypton particles are inherently heavier, considerably. So the answer here is krypton. This balloon's going to sink. This balloon's going to sink. This balloon's going to float. Most because the density of the gases are greater than the atmosphere, less than the atmosphere. So any gas that has a molar mass less than 28, which is that of basically nitrogen, will float, and things that do not have higher than that will sink. Which balloon will deviate from an ideal gas most likely? Okay, so in order to deviate from the deviate from an ideal gas, first of all let's talk about what an ideal gas is. I don't think let's add a page in here just so we can talk about that for a second. Okay. So a couple things about gases. One, they follow what's called the kinetic molecular theory. And it sounds really complicated, but really simple. This stands for how do particles essentially move. Okay, so a couple things you might want to note about this. One, they are traveling very fast. Number two, they are very far apart. There are a couple other little wrinkles to this particular thing, but these are the main two. These two are the premise for the overall theory that because gas particles are traveling very, very fast and they're very far apart relative to their size, there is little or no attractive or repulsive forces. Okay. So that means in a balloon, all the particles act like particles. All the particles act the same. I could have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles flying around the balloon, and all the particles essentially act like they're independent. travel around, and they don't even know that any other particles are there until they run into them, and then they bounce back off of them. So in this particular concept, what we have here, according to the kinetic molecular theory, is that essentially the identity of the particle does not matter. Okay, so the identity, okay, does not matter. Okay, so in this situation, a particle is a particle. The identity of the particle does not matter. This whole thing is called an ideal gas. Okay, so ideal gas is one that's traveling very far, very fast, very far apart, and there's no attractive repulsive forces between the particles, and therefore all the particles act the same, and every particle is just a particle. It doesn't matter if it's a carbon dioxide particle or methane or carbon dioxide. We call that an ideal gas. Okay. Now, a couple things about these ideal gases. Okay. First of all, I guess any particle can be an ideal gas particle. So we have an ideal gas particle, ideal gas, and we have what's called a non-ideal gas. Okay, so it's not like particle A, gas A is ideal and gas B is non-ideal. Has more to do with the conditions as to whether something is going to be an ideal gas or a non-ideal gas. Every particle, gas substance, we could alter the conditions and make it non-ideal, or we could alter the conditions and make it ideal. Okay, so essentially we have a situation where we can alter these conditions. Let's get a little container here. Make a box. Okay. Now, what makes something ideal? Okay. Well, first of all, they're very far apart, and they're traveling very fast. This is a situation where there's a very low pressure, meaning the particles are not colliding very often, and they're at higher temperatures. High temps. Again, they're traveling very fast. So, hot, that's fine. We got a particle here traveling very, very fast, and there's not many particles there, and therefore they're not that close together, and there's a low pressure. Why is there low pressure? Because there's not many particles there. They're not very close together. How do I convert a gas into a into a non-ideal gas? Okay, well, if I take this box, let's say it's even a piston, we'll put it in a, I guess, a piston, and I squeeze this thing down to the absolute smallest volumes. Okay, now again, all right, now, and so it's in smaller volumes, they're much closer together, and I make it colder, and this is going to cause this thing to slow down. All right, so now we're starting to violate some of our kinetic molecular theory. They're not traveling very fast anymore, and they are not that far apart. So the particles can have the opportunity to interact. Okay. Now, one kind of important idea here is that, okay, some particles are nonpolar. If you have a nonpolar substance or something with very low amount of intermolecular forces, well, these particles, even if you get them close together, right, they're still really not going to react much. So these guys are much likely to stay ideal. But if you were to make a gas, compress a gas like the one on the right, and this thing happens to have a significant amount of intermolecular forces, then it's a possibility that when these things start to get closer and slow down, that there could be some attraction. This goes straight off of Coulomb's law. Force equals the charge of the positive charge of the negative divided by the distance squared. Now, these top pieces here essentially are saying, are there some charges present here? If there are some charges present, then if we get them close enough together, they're going to generate some sort of attractive or repulsive forces. So whenever we're looking to compare which gases are more likely under the same conditions to act non-ideal, that's the one with the most intermolecular forces. That's an important concept. Okay. So, or again, let's try another little example here. This came up in the last couple of years. If we have, all right, if we have a container and we're compressing it, okay. So I'm taking this thing and I'm jamming it down into a smaller and smaller area. So let's say we have particle A and we have particle B. Okay, you got some A's in here and you got some B's. And we take this thing and we start shoving it into a smaller and smaller area and looking to see which one might liquefy first. Okay, so now 1, 2, 3, 1, 2, 3. Okay, so which one of these guys is going to liquefy first? Is it going to be A or is it going to be B? Well, it's the one that has the most intermolecular forces. Obviously, if A is water and B is carbon dioxide, well then in this situation, A can hydrogen bond and B can just London dispersion force. So the A is going to condense first and the B will stay gaseous longer. Eventually enough pressure could be produced, get them close enough together that they would be able to eventually, though carbon dioxide as well would turn liquid. That's a lot of pressure. So make sure you're clear on what an ideal gas is, what a non-ideal gas is, how gases become non-ideal, and which particles are most likely to act like either an ideal gas or a non-ideal gas based on the intermolecular forces present in that molecule. All right. Again, external factor. This is a review from previous discussions of temperature. We'll review it again here. Make sure you're understanding. Average kinetic energy is temperature. That's important. And this is the molecular velocity. So kinetic energy, 1/2 mv squared. Now again, it's the average. So some particles are sitting still. So this Maxwell's distribution of particles showing the distribution of fast-moving particles and slow-moving particles. Some are traveling very, very slow or essentially stopped. And some are traveling really, really fast. This is the average of the average velocity. Okay, and that's at 25. What about at 1,000? Okay, we have a new average. So on average, the particles are traveling faster because we're at a higher temperature. But the area under the curve represents the total number of particles. The total number of particles. So I want to make sure the area that I just highlighted in, the area under the curve, these are all the same area. So if I want to warm something up, I have to start at 0. You must touch the 0 because some particles inherently are not moving. But I need to in order to stretch it out to a larger average, I got to drop it down, like it can't go quite as high. And that's what it looks like. Okay. All right. Question. We have ourselves a couple samples of gases. And obviously, you'd be welcome to stop this video and try it. The gas particles in vessel 3 at 20 degrees Celsius are represented in the diagram above. The lengths of the arrows represent the speeds of the particles, which the following diagrams best represents the particles when vessel 3 is heated to 127. So we're warming it up. Take a moment, look at your options. A couple things here. We're always looking for wrong answers. But which ones might be wrong? First of all, didn't say anything about a chemical reaction occurring. I have 1, 2, 3, 4 particles, so I'm going to get rid of this guy because I got a lot more, way too many particles there. Here, we started breaking down into, it didn't say anything about anything breaking down. And there's 4 of them. 1, 2, yeah, they're all the circles there, but they broke apart. And here we have the top and bottom one. And the top one's got longer lines on average. And therefore, A is the correct answer. Longer lines means it's traveling faster. There we go. All right. Molecular velocity effects, diffusion, effusion. Okay. So what is diffusion? What is effusion? Let's just go ahead and jot this down here. So diffusion is a little bit different. Diffusion, because of the random movement of particles, just in open air, it's particles move, just random movement, and because of this random movement, it causes things of high concentration moving to areas of low concentration. Essentially, things are going to start spreading out. If you smell something in the air, it's because that gases are effusing across from an area of high concentration to an area of low concentration. Both of these pictures above here are examples of effusion. So this same thing can occur, but it occurs through gaps, whether in a membrane or if it's in a cell, called effusion. So effusion is the same thing through random movement. Only difference is we're going through holes. Things of high concentrations move to areas of low concentrations. Notice here I got a lot high concentration on one side, low on the other, therefore things move across. Osmosis is a good example of this. So what is osmosis? Well, just like, let's say here um, we have looks like a very low concentration here, and this isn't really showing osmosis, just showing diffusion across the membrane. But osmosis is the movement of water across the membrane to try and equalize concentrations. But I have lots of stuff on the outside, not so much on the inside, and stuff moves across the membrane to try and equalize on both sides. This is basically what it is. Okay. Here's an example of the formula that we use to do some math on Graham's law. All right, I'm just going to pull this thing away here so you can see it. All right. All right. So, what do we want to know about Graham's law of effusion? Works for effusion and diffusion, as far as I know. So, in this situation, all right. So this is the rate 1, rate 2 equals the square root of molar mass of 2, molar mass of 1. So the rate at which we effuse or diffuse correlates, not proportionally. Pay attention, because this square root here is gonna take the proportion out of it, not proportion. It correlates, meaning that fast moving particles effuse faster, but not proportionally, meaning that if you have a particle that's got moving twice as fast, it's not going to effuse or diffuse twice as fast. It will go faster, just not twice as fast. And keep in mind that for a given temperature, for a given temp, the rate of effusion is proportional to the mass. Heavier particles have a much lower velocity. Okay, so the velocity is directly proportional to the molar mass of the substance. So M stands for molar mass. Okay, molar mass. All right, so what we typically do for this, okay, is we combine this fraction into a single number. And I'll say, for example, um, let's say that gas 1 effuses twice as fast as gas 2. So that would be 2 over 1. And we just combine these two together. Now, since gas 1 is effusing twice as fast as 2, and I put the molar mass of 1 here and the molar mass of 2 here, I could solve at that point for a missing variable. If you give me this side here, I could know one of the molar masses and find the other one. I just need one missing piece. Okay, but typically we just combine this number into a whole number. Okay, a whole unit. So let's try an example. A balloon is full of air, N2NO2. What is the rate between the two? What is the rate between the two gases? So how much faster? Well, first of all, let's think of it this way. Which one's going to effuse faster? This guy has a molar mass of 28. This guy has a molar mass of 32. Now, because this guy's got a smaller mass, it's going to, for a given temperature, it's going to have a higher molecular velocity. So let's rearrange this. Let's say how many times faster is nitrogen going to effuse than oxygen? So I want to know the ratio of nitrogen to oxygen. Okay, and so this is going to be equal to the square root of the molar mass of nitrogen, because it's top and bottom, and the molar mass of oxygen. This is going to be 32, this is 28, and we can go ahead and solve it. And you'll see the math is already here, right here. So nitrogen will effuse 1.06 times faster than oxygen. If you turn it around, how many times, what's the rate of how oxygen effusing to nitrogen? It just gets reciprocal, and it's 0.93. So it's less, it's slower. Okay. So pretty simple plug and chug formula. Given some examples here, likely we will see more of that in the future. All right, so it says a 0.5 mole sample of helium and a 0.5 mole sample of neon are placed separately in two 10-liter rigid containers at 25 degrees Celsius. Each container has a pinhole opening. Which of the gases, helium or neon, will escape faster through this tiny pinhole, and why? Okay, now again, take a moment, pause the video, and take a look. Okay, so the answer here is that, okay, the faster moving particle is the one that's going to effuse faster. This happens to correlate to the one that's got the smallest mass. Therefore, helium is going to effuse or diffuse, depending on, in this case, it's diffusing faster. All right, so this one's out, this one's out, this one's out, and this is the only one left. And the main reason, as it moves faster, it hits holes faster. So hits the side containers of the wall faster. Everything's just happening faster because the particle's moving faster. All right. Pressure, external factors of pressure. Okay, so in this situation, let's just pull this off of here. All right, so sample question. A 2-liter rigid container has the temperature increased from 25 to 50 degrees Celsius. All right, so it's warming up. Using the principles of the kinetic molecular theory, explain what happens when the pressure inside the container. Okay, well again, it's a fancy word for moving particles, and we know that as we increase our temperature, we'll increase the velocity of the particles. So, how do we answer this question? Again, the kinetic molecular theory says just answer the question in terms of what's happening on the movement of the molecular particles. Okay, so in this case, we don't have more particles. We have the same number of particles. They're traveling faster, and therefore they're colliding with the inside containers of the wall more often. So the pressure is going to go up. Pressure increases. Particles travel faster, therefore hit the walls more frequently, causing more pressure. The particles are traveling faster, therefore hit the walls with more force, causing more pressure. There's two different units here. You want to make sure you understand both of them. Not only do we have more collisions, but the particles are traveling faster, so when they do hit, they actually produce a greater force as well. All right. These are some of the things we want to make sure that, that we have under our belt here. Ideal gases, non-ideal gases. How does a gas become ideal? All right. If you have to comparing two gases, which one is likely to become non-ideal as, let's say, pressure is applied? All right. So let's review this again. Ideal gases versus non-ideal gases. How do we get particles to start interacting? As I mentioned already previous to here, I didn't have the slide in front of me, but the charges from interacting forces are small and can and cannot be changed. Only way to change this is to change the actual substance. We can, however, get them closer together. So as we get them closer together, this force starts to ramp up. So I can increase my pressure, get them bounce off each other more. Pressure means the density of the particles, and lower my temperature, which slows them down. And I can now get this thing to happen here. This gets smaller, and therefore some force of attraction. All right, sample question here. A sample of nitrogen gas is most likely to display non-ideal gases. All right, so we want a container where the particles are able to interact with one another. You want it to be as high a pressure, that means they're close together, and you want the lowest temperature, because that means they're going slow. So we're looking for high pressure, low temperature. High pressure, high temperature, high pressure, low temperature, right here. Okay, that's the conditions that's going to most likely to deviate from the ideal gas. All right, which of the following substances is most likely to violate the ideal gas law? So again, we have two particles that we're talking for ideal gas particles that they don't interact. But this is kind of a misnomer because, I mean, any amount of attractions, particles typically have some attraction, okay, even if it's really small. So if you're going to have some attraction to particles, which of these is likely to have the case? We're looking for particles that have the most intermolecular forces. Again, that could be some sort of a hydrogen bond. It could be something of a dipole attraction, dipole-dipole, which is obviously the same as the hydrogen bonding, or it could be a large amount of London dispersion forces. Okay. And as I glance up on here, okay, the first thing I look for is a Steeler. Yeah, but this is cancels, nothing there. I have a Steeler, but it's a linear molecule, so it's going to be nonpolar. This guy has a Steeler. It would have a bent configuration, so it would not be linear. This one just exhibits dipole-dipole attractions, and therefore this is the guy that, given the ability to squeeze them down and slow them down possibly into a smaller container, if you get these close enough together, you might see some attraction between the particles. So it's got the most intermolecular forces. Just a quick little picture of benzene. No stellar and highly symmetrical. Okay. I think that's where we're stopping for this particular video. Thank you very much.